everyone. According to the schedule, we start our next talk, which will be given by Professor Mikhail Anikushin. And the title of the talk is Frequency Domain Conditions for the Exponential Stability of Compound Cocycles Generated by Delay Equations and Effective Dimension Estimates of Global Attractors. You have 25 minutes and 5 minutes for questions. You are welcome.
Here we go. My name is Misha. First of all, let me greet everyone and thank the organizers for the opportunity to participate in the conference. My name is Misha. I am a junior research assistant from the Department of Applied Cybernetics at the St. Petersburg University, and I would like to discuss my recent results concerned with the study of compound cocycles generated by delay equations and their applications to the problem of obtaining effective dimension estimates of global attractors. So let me illustrate the problem by means of the following scalar delay equation known as the Mikhail-Anikushin equation. There are some parameters, and it's well known that for a range of parameters the model may possess chaotic behavior. So where exists a chaotic attractor, and it's also known from the general theory the attractor has finite fractal dimension, but there are no known works that somehow estimate this dimension effectively. So we pose the problem of how to obtain effective dimension estimates for global attractors or just invariant sets which arise in the study of delay equations. So we're going to introduce the context in which we will work. Firstly, consider the main Hilbert space, which is a L-square space over the interval. There the measure is given by the sum of the Lebesgue measure and the delta measure concentrated at 0, which is the right endpoint of this interval. And consequently, each function from that space can be represented by its value at 0 and by its values in the interior, which is a function from the usual L-squared space on the interval. And we define a bounded operator in this space with the domain to be specified later by the formula 5. And here it acts on the boundary by taking vector-valued functional, which acts on the space of continuous functions. And in the interior, it acts just by taking the derivative. So we have an operator which is formally given by formula 6, and let us compute the adjoint operator of A. Here it's not hard to see that its interior action is given by the minus derivative. This is caused by the integration by parts in the integral which contains the first derivative. And this shows that symmetrization has kernel with finite codimension. This fact is related to the Liouville trace formula and shows that at least in the standard inner product we cannot use it to obtain effective dimension estimates. So we consider the following class of problems. Here we have a semi-flow on a complete metric space, possibly non-compact, and the class is given by formula 8. Here we have a vector-valued functionals on the space of continuous functions, and to the linear part where corresponds the functional A-tiled. There is also a measurement operator C, a control operator B-tiled, and the main non-autonomous part is described by a continuous field of linear operators from the measurement space to the control space, being some finite dimensional Euclidean spaces. And we assume that the norms of the corresponding operators are uniformly bounded. So the class is given like in formula 10, and such equations can be written as an abstract evolution equation in the main Hilbert space, just like in formula 11. And here we have the operator A from the linear part, which is associated with the operator A-tiled from here. And we can show that this abstract equation generates a cocycle xi in the main Hilbert space. And now let us consider its multiplicative extension to the m-fold exterior power of the main space. And we can state the problem of providing conditions for the uniform exponential stability of this cocycle xi m. Our method is based on the consideration of the cocycle xi as a perturbation of the strongly continuous semigroup generated by A, and the corresponding lifting of these relations to the extended cocycle. So the operator A is defined on the domain, which is given by the embedding of the usual space of Sobolev functions on the interval into the main space in such a way that its value of 0 agrees with its usual value as a Sobolev function. We can show that the operator A generates an eventually compact, strongly continuous semigroup. And then we can define the m-fold multiplicative extension of the semigroup to the m-fold tensor product of the main Hilbert space. And its restriction to the exterior power of the main space will be also a semigroup. So we can consider the generators for these semigroups, and in the case of the usual tensor product, the generator is called the m-fold additive compound of A, and in the case of its restriction to exterior power, the generator will be called the m-fold antisymmetric additive compound of A. We have the following theorem describing the spectra of these compound operators through the spectrum of the operator A. It's just the usual description for the sum of the eigenvalues of the operator A, and for each such value there is only a finite number of representations, like in formula 14. And moreover, we can describe the corresponding spectral subspaces through the spectral subspaces corresponding to the operator A. And if this subspace is non-trivial when it's intersected with the m-fold exterior power, then the corresponding eigenvalue belongs to the spectrum of the antisymmetric compound operator. We can describe the abstract tensor product of the main space through the Lebesgue space over the product measure, and this gives a correspondence between the abstract tensors and the functions on the cube of dimension m. And in the case of the exterior power, this gives an isometric isomorphism onto the subspace of antisymmetric functions, which will be discussed later in more details. To work with such a space, it's convenient to introduce the following sets, like in formula 20. These sets are called k-faces of the m cube with respect to the product measure. And in terms of these sets, we can decompose the product measure into the sum of codimensional Lebesgue measures on the corresponding sets, and the delta measure concentrated at 0. In terms of these sets, it's convenient to introduce the restriction operators, which restricts each function to this set. And we consider it as a function on the k-dimensional cube by omitting the fixed arguments. And to each such a restriction operator there corresponds the boundary subspace where all the operators but the fixed one vanish. When we have that, the tensor product of main space decomposes into a sum of these boundary subspaces. This figure illustrates the representation of the elements from the tensor product space for the case of twofold product and scalar functions. So here we have that each element can be represented by a function from the Lebesgue space on the square, two functions on the one faces, which belong to the usual Lebesgue space on the interval, and one value at 0. We can give the following description for the action of the m-fold additive compound of A in terms of the restriction operators. Here we have the diagonal derivative plus some measurements coming from the restriction of order k plus 1. We won't give precise definitions of these operators, but note that here we have the Sobolev-like space of the functions which have the square summable diagonal derivative. Now we are going to state our main technical result, which is concerned with some structure properties of solutions to the linear inhomogeneous problems as it's described by formula 25. And here the theorem states that the part of the solution corresponding to the fixed restriction operator can be decomposed into the sum of two functions which have some special structure. And we are going to discuss these classes of functions in more details. Firstly, we consider the following set as in Formula 27, and here we have the n-dimensional cube, which is translated along the diagonal vector with the components varying from 0 to big T. And then they define the function phi of t through the values of a function defined on this set, and we define it to be a function on the n-dimensional cube, but this cube is translated according to the time t along the diagonal vector. And in this case we say that such a function phi of t is a row adornment of x, or just what phi is row adorned. And then we consider the space of such functions and endow it with the following norm, which is a weighted norm of x in the L-square space. Now we're going to define twisted functions, for which we consider the diagonal translation semigroup in the L-square space on the cube, which semigroups acts by translations along the diagonal by formula 30. And for a given function y, like this, we define the function psi of t through the formula 31. We say that psi is a row twisting of y, or simple that psi is a row twisted. It can be shown that psi determines the function y uniquely. And we again consider the space of all such functions and endow it with the weighted norm of y. It turns out that the just introduced spaces are linearly independent, as is described by formula 33. And when we return to the decomposition, now given by the formula 35, we also have that the norms of these functions in the corresponding spaces can be estimated in terms of the initial data and the L-square norms over the time interval of the solution and the control function. And the constant in such estimate is uniform in time. We call such decomposition, as in formula 35, a structural Cauchy formula. Now we are going to discuss why do we need such decomposition. For this, let us consider two Hilbert spaces and a function gamma of bounded variation which takes the values in the space of linear operators between these two Hilbert spaces. And then for each j we define the operator Cj gamma, which takes a continuous function of k plus 1 arguments to the function of k arguments just by integration with respect to gamma and jth argument of the function. For example, if gamma generates the delta functional at minus tau, we have that these operators just put minus tau to the corresponding arguments. And we want to interpret the operator which acts by applying C gamma j to the functions of time with the values in functions on the k plus 1 dimensional cube. And of course, in general, this is not possible, but it turns out that such operator can be defined as a bounded operator. Then we restrict ourselves with the functions which can be decomposed into the sum of row adorned and row twisted functions, as in formula 38. And such functions are called row agalmanated. Now we return to the considered class of equations and its abstract form in the main Hilbert space described by formula 40. And this formula shows that the cocycle psi on the infinitesimal level is given as a boundary perturbation of the operator A. And we have a similar statement for its multiplicative extension, namely the cocycle psi m, to the tensor product. And here we also have the linear part given by the m-fold additive compound of A. And the perturbation is also a boundary perturbation, but in this case we have the composition of the boundary into boundary subspaces. We are going to discuss these operators which arise in this formula. We start by representing a vector-valued functional from a space of continuous functions through a matrix-valued function of bounded variation, like in formula 42, and then we can associate with such a function of bounded variation the linear operator from the tensor products of certain spaces, which acts by the measurement over the jth component of the tensor product. This correctly defines a linear bounded operator, which also depends on the argument as a function of bounded variation, and then the measurement operator, which are also in the theorem, is just the operator Cj gamma with this gamma and the measurement space. It's much easier to define the operator f prime j of p. It's also an operator which acts on some tensor products by the action of f prime, which is applied to the jth component of the tensor product. And we use the same notation to denote the operator between spaces of functions taking values in these tensor product spaces, where this operator is applied pointwisely. And then we define the boundary operators, which take a function of k variables to the element on the boundary subspace corresponding to the multi-index j1, jk, just by formula 45. Now we are going to associate a control system in the tensor product space. For this, we define the control space given by the orthogonal sum as in formula 46, and we define the control operator through the formula 47, and here we use the boundary operators which we defined previously. And then with the pair given by the m-fold additive component of A and the control operator, we associate a control system by the formula 49. And we have to consider its antisymmetric analog. For this, recall that for our main space, the m-fold exterior product is naturally isomorphic to the subspace of antisymmetric functions, and recall that such functions satisfy the relation given by formula 49 for each permutation, and almost everywhere with respect to the product measure. And when we apply the restriction operators to this relation, we obtain the antisymmetric relations between k faces for the same k, like in formula 52. And with such relations, we can associate subspaces, like in formula 53, corresponding to the functions which are non-zero on the k faces and satisfies the antisymmetric relations. It may happen that some of these subspaces may be trivial. For example, for scalar case, there is only two subspaces which are non-trivial. If the corresponding space is not trivial, we say that K is proper. From this, we can define the control space for the antisymmetric case. For this, we consider the tuples from the control space satisfying the relations from the formula 55. And then we define the antisymmetric control space as a set of tuples from the control space, which satisfies these relations for proper K and supposed to vanish for improper K. Recalling the system describing perturbations for the compound cocycle, we can associate with it the control system given by formula 58. And here the control operator is defined on the antisymmetric control space by the restriction of the control operator from the usual control space. We can relate the just introduced control system, which is now given by formula 60, to the original system presented by formula 59 through the closed feedback. So we put instead of control function the closed feedback from the original system. And then the corresponding solution satisfies the quadratic constraint. That means that the following quadratic form takes non-negative values on the corresponding solution. We are going to specify the domain of definition of this quadratic form and to generalize such quadratic constraints. For this, we need to consider the measurement operator Cj gamma in a wider context. For this, we define the space of all functions on the M-cube such that its restrictions to the shifted m-1 faces can be represented by a continuous function when this set identified the m-1 dimensional cube. And this space can be naturally endowed with a norm from the formula 63 that makes it a Banach space. And it's very important that the measurement operator Cj gamma can be extended to a bounded operator from that space to a space of L² summable functions on the cube. From these spaces we define the intermediate Banach space by formula 64. This space can be embedded into the tensor product of the main space, and we have the inclusions from the formula 65, and we have analogous inclusions as in formula 66. Then we define the measurement space by the formula 67, and the measurement operator in the tensor product is now defined by formula 68. And here we use the measurement operators on the right hand side are defined on the corresponding parts of this intermediate Banach space. For the antisymmetric analog of these spaces, we introduce the relations as in formula 69, and we put the antisymmetric measurement space as the set of tuples from the measurement space which satisfy the relations for proper k and vanish for improper k. And then the antisymmetric measurement operator is just the restriction of the tensor measurement operator to the antisymmetric intermediate space. And then in these terms we can write the quadratic form in a compact way, just like in formula 72. We can generalize the quadratic constraints as follows. We take a bounded quadratic form of antisymmetric measurement tuple and antisymmetric control tuple. And then we just put the quadratic form via the formula 73. And we say that f is a quadratic constraint if it takes non-negative values. In the case we have the closed feedback satisfied, just like before. Very important property of the intermediate Banach spaces is just they can provide the estimates for the norm of the resolvents in these spaces, just like in formula 74. Now we introduce the associated frequency inequality. Here we take a vertical line with the fixed real part, which avoids the spectrum of the antisymmetric M-fold additive compound, and for a given quadratic constraint we consider the frequency inequality given by formula 75. Note that here we use the Hermitian extension of the quadratic form. And now we can formulate our main theorem that states that if for a quadratic constraint the frequency condition is satisfied when there exists a bounded self-adjoint operator such that its quadratic form will be a Lyapunov-like functional for the compound cocycle considered in the antisymmetric space, just like in formula 76. And in the case we have a certain dichotomy properties of the antisymmetric additive compound, we can control the sign properties of this quadratic form. When there is no spectrum to the right of the vertical line and the exponent nu0 is positive, when we have conditions for the uniform exponential stability, just like in formula 77. In a more general situation than the base system is a flow, we obtain conditions for the existence of gaps in the Sekers cell spectrum of the compound cocycle. Let us discuss some problems arising in the case of numerical computation of frequency inequalities. Here we suppose that the control space and the measurement space are the same, and that the operator f prime is a self-adjoint operator which satisfies the condition like this. For the proper quadratic form, the associated frequency inequality takes the form as in formula 79. Here we use the additive symmetrization of the transfer operator, and we have to compute this inequality. We can approximate this value just by taking truncated by some projector values, like in formula 81. And it can be shown that these truncated values converge to the desired value for each omega. But this convergence depends on the fixed omega, and the wider interval of omega we want, the larger n we should take. Moreover, computing such approximations requires solving the resultant equation, that is a first-order PDE, in the cube with boundary conditions containing both partial derivatives and delays. We have to compute this resultant equation for each basis vector. For large number of basis vectors, we will usually deal with highly oscillating functions that cause high computational errors. And unlike in the case m equals 1, this value do not vanish as omega tends to infinity. But in concrete examples, it seems to display an asymptotically periodic or almost periodic pattern. So here you see the list of my works related to the topic. That's all. Thanks for your attention, and if you have any questions, you're welcome.
Thank you for a very informative talk. Questions, please. Questions? Okay, then I have a question. From your point of view, what is the most important result in that talk? Because the talk was really informative. So from your point of view, what is the most important here?
The most important is the last theorem on the existence of quadratic Lyapunov functional and its consequence for numerical computation, which show that the problem is highly complex and it's very hard to compute these inequalities even with the help of computers for the chaotic systems with chaotic attractors. So like this.
I see, thank you. More questions? Okay, then let us thank the speaker again.